A sand and gravel plant, at a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. So somewhere up here in the air, there's a conveyor belt, and sand is falling off that conveyor belt, and as it does, it forms a cone. That's my very best job of a conical sand pile. At a rate of 10 cubic feet per minute, what quantity is that 10 cubic feet per minute measuring?
How fast it's falling?
Okay, it's definitely a rate. It's not just a volume, but it's the rate at which the volume is changing. So what symbol will we assign to the rate at which the volume is changing?
dr over dt.
dV over dt. You could use R if you make a note, let R stand for volume, but that would be weird. Let's just let V, that's okay, let's let V stand for volume. And the change in volume with respect to time is 10 cubic feet per minute. All right, we're always going to draw a picture when we can. We're going to write the rate that we do know, and then we're going to write what it is that we're looking for. Find the rate of change in the height of the pile. What does that sound like that we're looking for? dH over dt. It says find the rate and change in height. That's dH over dt. And then at some particular moment in time when h equals 15. All right, the three parts of every problem, right? What I know, what I'm looking for, and an equation. What is an equation that involves both volume and height of a cone?
1/3 pi r squared h.
All right, that's V equals 1/3 pi r squared h. Did I hear you right? Okay, all right, so everyone had that formula or that equation? The problem with that equation is it has three variables, and I'm not in multivariable calculus yet. I need to get it down to just an independent variable and a dependent variable. Either I have to write r in terms of h, or I have to write h in terms of r so that I only have one independent variable. Well, let's go back to the problem and see if there's a fact that I missed. The diameter of the base is approximately 3 times the altitude. Give me some symbols for that. Write an equation that would say diameter is 3 times altitude. Remember, altitude and height's the same thing. So what's that equation? D equals 3h. And I believe I did this much for you Friday before you left. I gave you this hint. This is not really helpful because my equation doesn't have d's in it. It has r's in it. But in place of diameter, I can just say diameter is the same thing as twice the radius. And then, do I want this equation to end up with r's in it or with h's in it?
H.
H's, because I'm given a particular height and I'm looking for the rate of change in height, so it's the r that I want to get rid of. What is r in terms of h?
3 halves h.
3 halves h. If you solve for r, you'd divide both sides by 2. And the radius is 3 halves of the height, or 1.5 times the height. So you can put that in place of the r. R is 3 halves h squared times the other h. And that's 9 halves, or I can go ahead and say 9/4 times 3 is just 1/4. Nope. 9/4 is 3/4. And h squared times h is 8 cubed. Let me see if I did that in my head correctly. That's 9/4 times 1/3 is 3/4. So is that what you got for an equation for V in terms of H without any R's in it? Yes or no, this is okay?
Yes.
Okay. Now, my folks who asked for that, John and somebody in Harriman, was it getting that equation that was difficult or finishing the problem after you already had that equation that was difficult?
Getting it there.
Okay, so you plugged the wrong, you did the 2/3 that you said instead of 3/2, right? How about my Harriman person? Could you finish it? Could you finish it now?
Yeah.
Okay, all right, that was the hard part. We can only have an equation with one dependent variable and one independent variable before we differentiate both sides. All right, let's go on and finish up 3.7 today. I'm glad we had 2 days to work on that. The next problem I had circled was number 24. A trough is 12 feet long and 3 feet across the top. I purposefully am hiding the figure so we can have to draw it without looking at it in the book. My very best trough that's 12 feet long and 3 feet across the top, its ends are isosceles triangles with altitudes of 3. Wow. Wouldn't it be cool if I can draw a trough? Y'all know how limited my artistic abilities are. Like a water trough for cows.
Okay. I know what them look like.
See, I was raised on a farm.
Me too.
Good people.
I'm buying more chickens today.
What?
I'm buying more chickens today.
Oh,
Chicken.
buying more chickens. Don't do it.
I love chickens.
Man, I was raised on a chicken farm. You do not want more chickens.
Oh, they're horrible.
No, they lay a lot of eggs and they have good meat. That's why I like them. They're gross.
All right. Okay. Oh, I'm so proud of me. Look at my trough.
Yeah, that's pretty.
All I do is draw the 2 triangles. I don't know if y'all can see when I point at the TV or not. Draw the 2 triangles and then connect their vertices.
How's that staying stationary? It had to have something to stabilize it. Because you know it's kind of like a V on the ground. It's going to tilt.
I don't know what you're saying, but I'm pretty sure it's not relevant, so be quiet.
All right.
It needs legs, is what he's saying.
Okay, there's my trough. It is 12 feet long. Obviously, this is not to scale. That's my 12-foot long trough. And 3 feet wide across the top. Not to scale at all. My 3 looks bigger than my 12. And the altitude is 3 feet, which just means the trough is 3 feet deep. Now, does it make sense that at any point in the water level, let's say that's my water level right there, does it make sense that since when the trough is full, its width is the same as its depth, then at any water level, its width will be the same as the depth. That's based on similar triangles. If you have a big triangle, big isosceles triangle, whose let's say ratio of width to height is 10 to 5, then if I have a smaller triangle whose width is 6, its depth is going to be 3, because those are similar triangles. The ratio of width to altitude is going to be, the width is always going to be twice the altitude, no matter how high you make the triangle. So if the ratio of width to height when the trough is full is 1, then the ratio of width to height at any point is 1. In other words, the base is the same as the height for any water level. All right, back to the problem. 12 feet long, 3 feet across, and the depth is 3 feet, which means the base is the same as the height. Now, in the A part, we have water is being pumped into the trough at 2 cubic feet per minute. What is that a measurement of? 2 cubic feet per minute.
Volume.
Not just volume, but rate of change in volume with respect to time. So the symbol we're going to use is dV over dt is 2. And we're asked, how fast is the water level rising when the depth h, you could call it depth of the water or height of the water, it's the same thing. The depth of the water is 1 foot. What symbol will we use for how fast is the water level rising? The height of the water or the depth of the water. Use dH over dt. Find dH over dt, and then we're given at some particular h equals 1. What formula should I even try to find in the back of the book? Is there a volume of a trough formula in the back of your book?
Triangular prism.
That is a triangular prism. All right. Does the back of the book have a formula for volume of a triangular prism?
Maybe.
Maybe. But if it doesn't, I can find, I know that volume has 3 components, length, width, and height. So the area of one end times the length of the trough would give me all 3 of those components. That would give me the length and the width and the height. Or I could Google volume of a triangular prism. All right, either one would be okay. But if I don't have Google with me, what is the area of this triangle? 1/2 base times height. So let's see. I'm going to write some words here to help you. Area of triangle times length of the trough. 24. The area of the triangle is 1/2 base times height, and the length of the trough, no matter how deep the water is, it's going to spread from one end to the other. It's always going to be 12. Regardless of the height and the width of the surface area of the water, the length is always going to be 12.
Did you refrigerate that to make it into? Would that be like anti-differentiation on getting it into the triangular prism? Because remember how the diameter of a
Oh, I know what you're saying. I would have to think about that a minute because the examples I gave you, they only had one independent variable, like surface area of a sphere and no, I gave you circumference of a circle and area of a circle, only one independent variable.
Okay, gotcha.
All right, two things I notice here. One is half of 12 is 6, and the other thing is B and H. We already made a note up here, B and H are the same thing. So I want my variable to have H's, not B's in it.
H squared.
Yeah, just H squared.
Could it be 6H squared?
Uh-huh. How about that?
Okay.
You good?
So far so good?
Is that
Questions?
Is that a 2 for the height or a 3? Because it looks like you wrote a 2.
It's a 3. The problem told us that the altitude of the isosceles triangle was 3. It started looking like a 2 when I drew my little water level line across there.
Okay.
All right. Now we have a formula that only has rates that, or variables for rates that we either know or are looking for. So we're ready to differentiate with respect to time. What's the derivative of the left-hand side with respect to time? dv over dt. What's the derivative of the right-hand side with respect to time?
12H times dv over dt or whatever.
D what?
D something.
D.
R.
No. Why would we have an R? We didn't have an R in the original equation. dH over dt. Which one of those two rates do we know? dV over dt is 2. We're solving for dH over dt when h is 1. So what is dH over dt? 1/6. Make me a sentence for what that dH over dt equals 1/6 actually means. Make me a sentence that tells me that you know what dH over dt equals 1/6 means.
Say it now.
Yes. Yes. I need a sentence that a farmer would understand. A sentence that somebody who actually owned a cow trough would understand.
The height of the water is increasing by 1/6 feet per minute.
All right. Ooh, I got it perfect here from Mr. Warren. The height of the water, or actually you'd probably say depth if you're just talking to somebody, the depth of the water is increasing at a rate of 1/6, and what was the units on that?
Feet per minute.
Yes, that is feet per minute, because this is a height. This is a height, not a volume.
Yeah, I did that first too. I put the 3 cubed per minute. I'm like,
Yep.
wait a minute.
That means,
Could you say 2 seconds or 2 inches per 10 seconds?
You just look at the original. Just see it.
only if you wanted to hurt my brain.
Okay.
Water is rising at a rate
I'll work on
of 1/6 of a foot per minute. Or now that I'm through writing, tell me what you said, 1/6 of a foot per minute, or you said what?
2 inches per 10 seconds.
2 inches.
Oh, no, it wouldn't be 2 inches per 10 seconds.
Oh yeah, you're right. 2 inches per minute.
Yes,
Which
two
would be- hold on.
2 inches per minute.
So over 60, 130. An inch for every 30 seconds.
All right, stop
An
it.
inch for every 30 seconds, which means half an inch for 15 seconds.
What about 4 of an inch?
We know
You
who
could also put that as it increases 1 foot every 6 minutes.
we know who had Monster drink for breakfast.
I don't like monster.
No, just chat.
All right, that's the A part. Let me see if I actually want to do the B part. I know that drawing the picture is always the hardest part. Let me just ask you this. We're not going to write down the B part, but I would still use the same equation. I would use the volume is 6 times height squared because my picture is not going to change in the B part. I'm looking for dV over dt. Find the rate at which water is being pumped into the trough. That's dV over dt. When dH over dt is 3/8 of an inch per minute. Let me see if you can tell me what the most common mistake would be.
They would.
Put 3/8 for height.
Put 3/8 for the height. What were our units on height? Feet per minute. You would have to change 3/8 inches per minute to feet per minute. Your units have to match. If your rates are given in feet per minute, then your height has to be given in feet per minute. So you would say 3/8 inches divided by 12 and put that in the place of dH over dt. All right, just change inches to feet. Yes.
As a thought,
Yes.
if you plug in 3 feet per minute and an H of 3, you would be able to find how much water you need to pump into it per minute. I'm trying to think of how to word this. You'd be able to find how much you need to pump into it to get it filling up to full in a consistent period.
Yes.
Yeah.
Yeah. Cool.
So we're changing inches to.
Yeah. I'll write this hint for B part down. Even though we're not going to do it. We're given dH over dt is 3/8 inch per minute. So dH over dt is 3/8 divided by 12 or times 1/12. Would be 1/32 feet per minute. As long as you put that in place of dH over dt instead of the 3/8, you could do the B part. All right. Let me see if I can figure out how to show you something on the computer instead of Elmo, perhaps. This is the coolest thing I found this weekend.
Just follow my mind. Well, 16 would be 3/8.
Hey, I got it in one try. Here's, oh, please, 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 go away. Here's what I do when I'm through pulling up weeds and lighting fires at my house. When I get tired of burning stuff, then I Google related rates, animations, and it just so happened that the coolest I found were at Temple University. I love that people put their good stuff on the internet for free. We're about to do a problem involving raising a ladder. Here's the animation I want you to see. Ooh, by the way, let's look at the conical sand pile. Number 21 that y'all asked me in the homework. Sand is going to go up this conveyor belt and then drop onto a conical pile. Here's the sand going up the conveyor belt, dropping onto the pile, and where's my X's and Y's?
That's to form the pile first.
I'm sorry, what?
It's gonna form the pile before it does.
Oh, okay. More sand, more sand, more sand. Piles higher, piles wider. All of the rest of them give me an XY chart that I can see changing. Huh?
That is.
Is that really sound of sand falling? And this one isn't as good as I wanted it to be. It's not showing me.
Maybe it's because the question is.
Yeah. Okay, let's play like I didn't do that. There's nothing I want to say about that one. There is something I want to say about the one we're fixing to do, raising a ladder up a wall. The ladder is pulled up the brick wall at a steady rate. I'm going to pause it so I can say something right here. Notice that the ladder is always 10 feet long. It's being pulled up against a wall, but the length of the ladder is not going to change. What is going to change is the distance the opposite end of the ladder is from the base of the wall, and how high the other end of the ladder is up the wall. We're always going to let X stand for a horizontal distance and Y stand for a vertical distance. So X is going to be the distance the base of the ladder is from the wall, and Y is going to be how high up the wall the other end has made it. All right, if you understand what your X's and Y's stand for, watch these. As X's get smaller, that means as the one end of the ladder gets closer to the wall, Y's get bigger, the distance the ladder has climbed up the wall gets bigger. As X's get smaller, Y's get bigger, but the length of the ladder is always 10 feet. And if it had gone just a little bit farther, if the top of the ladder made it all the way to the top of the wall, that means if Y is 10, what would X be? X would be 0. The other end of the ladder would be up against the bottom of the wall. When the top of the ladder is 10 feet high, then the bottom of the ladder would be flat up against the wall.
Only if that wall was 10 feet tall.
That's a good point.
No, it wouldn't have. No.
Because if you have a diagonal ladder, you can have it at the top of the wall,
Uh-huh.
as long as the ladder is longer than that wall.
Or even if the wall is shorter than the ladder, the bottom of the ladder would still be flat against the wall. The top of the ladder would just be sticking up above the wall.
That's not safe.
And John says that's not safe, which makes me wonder what what experience John has had with ladders in the past. He might have a good story to go along with that. All right. The important thing to realize here is that as the ladder gets higher up the wall, as your Y's get bigger, your X, your distance the bottom of the ladder is from the wall, gets smaller, but the ladder itself is not changing. The length of the ladder is not changing. So let's see if that helps you visualize number 26. Back to Elmo.
The test you're gonna give us over this is gonna be full of word problems.
Yes, 20 word problem. No. Oh, 3 word problems worth 33 points each.
Sweet. Let's go where we can make 100.
Yep. I'll give you 1 bonus point for just having the nerve to show up. A construction worker pulls a 5-meter plank up the side of a building. So instead of a 10-foot ladder, we have a 5-meter plank. But still, he's pulling it up the side of the building under construction by means of a rope tied to one end of the plank. The book has been kind. Mr. Larson's been kind and drawn a picture for us. I'm not going to be kind on the test, so practice drawing your own picture. Draw your very best wall. My very best wall. My very best plank being pulled up that wall. And the plank is going to stay 5 meters long. Let's let y be the vertical distance, or if it made more sense to you, you could let you could let h be the height of the ladder up the wall. That would be fine. I'm going to let x be the distance the other end of the ladder is from the wall. Is there going to be a plank pulled up the wall formula in the back of the book? No. What formula or what equation could possibly relate that x, y, and 5? It's a triangle. Specifically, it's a right triangle. So what equation do we know relates the sides of a right triangle to that plank?
Pythagorean theorem.
The Pythagorean theorem. What is the equation?
A squared plus b squared equals c squared.
X squared plus y squared equals 5 squared. Or
Would X and Y vary?
what?
I don't know. Never mind.
Okie dokie. X squared plus y squared equals 25. Do both x and y depend on time since dude started lifting the ladder? Yes. Yeah. The longer he's been lifting, hopefully the higher one end of the ladder is and the closer the other end is to the wall. So both of those are variables that are functions of time. Do I have to have either the x or the y by itself before I can differentiate? No, because I'm differentiating implicitly anyway, being as I'm differentiating with respect to something other than just x or just y. So what is the derivative of that equation with respect to t?
2x plus 2y over dy over dt.
Okay, Miss Kayla, you didn't say your dx over dt, but you were thinking it?
No.
Okay, they're both differentiating with respect to time, so no matter what variable you're differentiating, you're going to have d that over dt.
Gotcha.
All right, and then the next term, 2y dy over dt equals what? 0. My biggest mistake is forgetting the right-hand side is going to be 0. Now, actually, I got excited to start differentiating and forgot to write down the rate that I was given and the rate that I was looking for. So let's go back to the original problem. Assume the opposite end of the plank follows a path perpendicular to the wall. That just means this end is coming in perpendicular to the wall. And the worker pulls the rope at a rate of 0.15 meters per second. Is that the dx over dt or the dy over dt?
dy.
The rope is in on this end of the ladder, pulling it up. So that's dy over dt is 0.15 meters per second. How fast is the end of the plank sliding along the ground? That's dx over dt.
Negative.
Find dx over dt when it is 2.5 meters from the wall of the building. Is that x equals 2.5 or y equals 2.5? That's the distance the end of the plank is from the wall. That's your x. When x equals 2.5. Now the only new twist in this problem, I've already differentiated. I have something to put in the place of x. dx over dt is what I'm looking for, so I don't have to put anything in its place. I have something to put in the place of dy over dt, but I don't have anything to put in the place of this y. What am I going to do about that? If I know x equals 2.5, I can find the y that goes with it from the Pythagorean theorem. I'm going to say when, this is just kind of a side note, when x equals 2.5, y equals the square root of 25 minus 2.5 squared. Y is the square root of the hypotenuse squared minus 1 of the legs squared. That's 25 minus 6.25. I believe somebody's going to have to calculate that for me.
Take the square root. It's square root.
It's the square root of 18.75, which is
You know what?
ugly number.
Let's keep this answer as exact as possible and just use square root of 18.75. Because if we punch it on the calculator, that's definitely going to be a decimal that goes on and on and on. Now we have everything we need to substitute into our differentiated equation and solve for dx over dt. 2 times x is 2.5, times dx over dt, that's what we're looking for, plus 2 times the square root of 18.75 times dy over dt, that's our 0.15. That equals 0. And we're solving for dx over dt. So I'm going to say 2 times 0.15 is 0.3, and subtract 0.3 square root of 18.75 from both sides. And then divide both sides by 2 times 2.5 is 5. Isn't it what? Let me double check. No, 2.15 cents is 30 cents.
Okay.
I always do decimals to 2 places as money, and decimals with 3 places I have to write down. I can't do them in my head.
And you can rationalize that further if you want to get rid of the decimal in the top.
Well, since I just, I'm through calculating, I just want my answer now, I can punch it straight as that on the calculator and round to whatever my boss wants me to round to.
I don't like.
Well, I'm not going to leave it like that. But I come up with negative 0.26, I believe. Anybody second that?
Yeah.
Yep.
Okie dokie. Negative 0.26. And what are the units on that negative 0.26?
Oh, what were
Meters per
meters per
Meters
second.
per second. And I'm so happy to have the answer in the back of the book. I don't care what it means. But you need to care what it means. Make me a sentence that tells me what the heck I have just found.
When you're pulling the rope 15 meters per second,
Uh-huh.
the change in X is going to change from negative 0.26 meters per second.
You know what? The person, the foreman of this job, she doesn't know what X is. So you just made a sentence that doesn't make any sense to her.
The rate of change of the distance
Take calculus.
of the ladder to the wall is.
You would probably just say, what is that
The ladder is
distance?
approaching the wall at 0.26
Yes.
That's
meters.
beautiful. That's beautiful. You would say the base of the ladder is getting 0.26 meters per second closer to the wall.
Because the negative 0.26 just means it's getting smaller.
That distance is getting smaller means the base of the ladder is approaching the wall. So I'd say base of ladder is approaching wall
I say golf clap.
at 0.26 meters per second. Why are we not saying negative 2.6 meter or negative 0.26 meters per second?
You can infer that the distance is getting smaller.
Yeah, we've already said the distance is getting smaller. We don't want to say it's getting negative or at a negative rate.